Good afternoon, everybody. Welcome to the Managing Microservices and Service Mesh session. We have 4 papers in this session, and our first speaker is Sachin Ashok, and he is a PhD student at the University of Illinois at the Urban Champaign, where he is co-advised by Professor Bryton Godfrey and Professor Radhika Mittal. Sachin's current research interests include performance optimization and monitoring for microservice-style systems.
Thank you for the introduction. So hello, folks. I'm Sachin Ashok, and I'm a graduate student at UIUC. Today, I'll be talking to you about TraceWeaver, which is all about distributed request tracing for microservices without application modification. This is joint work with folks at UIUC as well as IBM. All right, so we begin with sort of observing the evolution of software. So software used to be built like monoliths where you have these different components which used to talk to each other through sort of function calls. Now, for reasons of scalability and easier deployment, you have these microservice-style systems where each component is independently deployed and they talk to each other through network calls instead of function calls. Right, so all that is great for software, but debugging such microservice-style systems is extremely difficult. So imagine you have a microservice-style system as shown here, where you have a bunch of requests that you want to service. So typically, these requests follow a very convoluted path through the microservice in order to get service. So this is usually a nightmare from the point of view of observability. This is fundamentally because many complex systems must interact to produce even a single end-to-end response. So this might seem trivial, but let me show you a more sort of convincing example. So this is the Netflix microservice topology, and as you can see, it's usually a multi-hop DAG with many, many stages. So debugging issues for a single request usually requires end-to-end visibility across multiple services in your system. All right, so that's exactly where end-to-end request tracing comes in, but let me give you a brief primer. So a span in distributed tracing is an individual unit of work which starts with the request arriving and ends with the response being sent out. So in this example here, you have 2 kinds of spans. You have the red and the yellow. The point of end-to-end request tracing is essentially to put together spans of the same type so that you can have a coherent trace of execution. So now you can go and see exactly where the yellow request for the span had trouble in processing and so on, right? So these end-to-end traces are extremely useful, and they provide a lot of visibility because they can answer queries like, which service contributes most to the delay experienced by the slowest 1 to 2% of the requests? Or for example, which client requests are causing out-of-memory errors at a service X? Or for example, how much time did high-priority requests take at a particular service? So you need to actually trace these requests through in order to be able to answer these end-to-end queries. By the way, end-to-end tracing is just one debugging strategy. There are other related ones. So for example, you have service dependency mapping, where the idea is to infer coarser service dependencies, like the fact that service A depends on B and C, whereas B and C do not depend on A. You also have span or service level analysis, where the idea is you can analyze these fragmented spans or service level information. Like you can ask questions like, what is the processing delay for the span? Or you can ask things like, what's the processing delay for all spans that arrive at this service? So these are not end-to-end queries, right? So the problem with the first approach is that it cannot do finer-grained request-level tracing. And the problem with the second is that it cannot do end-to-end analysis. So hopefully everybody agrees that end-to-end traces are a good thing to have. So what is the main challenge, right? So the main challenge is, imagine you have 2 requests arriving at the front end, and let's say the front end issues 2 back-end requests as a consequence. Now, the challenge is in mapping these requests. So for example, is this the right mapping, or is this the right mapping? It's kind of hard to know this mapping without knowing the intricacies of a given application, right? And this problem is exacerbated in every single service the request interacts with. All right, so the way this is done in the industry today is something called header propagation, where when a request arrives at the front end, a global controller would add IDs onto it, and when subsequent backend requests are generated, you would copy and propagate these IDs onto them. But the main problem with this is that you have to go and modify all the applications in your system to add these tracing errors and propagate them. It might seem trivial in this diagram, but this is quite hard to do when you have a large code base in an enterprise where every single function signature needs to be modified to sort of propagate these IDs. All right. And also in a large enterprise where you have a lot of loosely coupled services, it requires buy-in from all of these services, which can be pretty hard. And even when you have systems where you can actually do this modification, you have legacy and proprietary applications where making this change is quite difficult to begin with, right? So for all of these reasons, we note that header propagation can be a pain, which results in a very low rate of deployment in the industry. So we ask a very academic question. So we ask, can we enable approximate end-to-end request tracing without application modification? And what we see is that it's already good enough for a lot of use cases with the accuracy we get by doing this transparently. All right, so our general approach is as follows. So if we start with capturing all the externally observable data that we can get for free, so easily accessible data about incoming and outgoing spans. So for example, like timestamps, the type of the request, and so on and so forth. So what this data gives us is that it gives you a list of all the incoming span and the outgoing span. So you have a collection of all this data. Then, for every given incoming request, you can now map it to any outgoing request, right? So you need to basically have a way to prune this search space. So basically, our task is to automatically identify the constraints associated with an application and use those constraints to determine which outgoing spans or requests we must consider as potential mappings, which are what we call as candidates. Once we do that, even then, after pruning a lot of these candidates, we're left with more than one candidate per incoming span. So we need a way to score and rank these candidates, right? So because you need to choose between all the valid candidates. So we have a way of doing that. And then finally, once you have done that, once you have a set of valid candidates for each incoming span, you need to run joint constraint solving, which basically tries to say, can you find an answer or an assignment of incoming span to outgoing candidate in such a way that all incoming spans are guaranteed to get one answer, and that answer is like a very good answer, meaning that it gets a good score for each of those mappings. All right, so we start with capturing externally observable data, like timestamps and request types. So we use easily available middleware like eBPF hooks and so on to like capture this information. So for example, T1 in the diagram is the timestamp at which a request arrives, and T6 is the timestamp at which a response goes out. Similarly, the endpoint which that request hits, which is the IP:port/API, is what we use to classify a request to be of a particular type. So all of this information is grabbed automatically by using this middleware option. Please note that other middleware options like service mesh proxies or Wireshark or TCP dump agents are good candidates to capture this type of information as well. Then once we have this information, we need to like prune our search space. So the first strategy we try is to create request-response mappings, right? So the idea here is that even though we cannot map the incoming request to the backend request, we can map that incoming request to its corresponding response. Because if you know the protocol that the request follows, then doing that mapping is trivial, right? So for this, we use per protocol parsers, where we identify what protocol a request is following, and then we map it to its corresponding response. So for example, in HTTP2, if you know the stream ID of the request, requests and responses are aligned in FCFS order within it. So it's easy to like map requests to responses. However, I should reiterate that this does not solve the mapping problem because we can still not map the incoming spans to the outgoing spans. So that still remains a challenge. All right, so the next strategy we try is to use the call graph that a particular request type follows. So for example, that might be the microservice call topology, but a separate sort of subset of this topology is what a particular request might traverse in order to do its job, right? So how we get this sort of call graph is by running queries in a developer environment. So in a developer environment, you can take a request of a particular type. We can run a query and see which services it interacts with to know exactly what call graph it follows. So since there are no other requests, there's no sort of no ambiguity in identifying that. All right. And what this information also tells you is that first, it tells you that which request coming from which services should be mapped to which request going to which other services. And it also tells us, for example, here, that a request that comes to X should not be mapped to Y if a request is of this type, right? So it gives us this two pieces of information which we can use to prune. Next, we also use causality constraints. So we identify two kinds of constraints. One is the parent-child constraint, where the idea is that for an incoming span, which is the blue span here, the request must arrive before the backend request goes out. Similarly, the response for that backend span must come in before the response for the parent span goes out. These are like simple parent-child constraints. Similarly, you have sibling constraints. So for example, if A talks to B and C in order to service its request, in what order does it talk to it? So for example, in this case, the request to B must be invoked and the response must come back before you talk to C, right? Those are the sibling constraints. All right, so let me show you a quick example how we might use this. So for example, let's say you have 3 requests coming in, red, blue, and green, and let's say you have 3 backend requests, which are in gray because we have not mapped them yet, right? So what constraints tell us is that, for example, here, the third gray span cannot be mapped to the green span because the response for the gray span came in after the response for the green span has already gone out, right? So parent-child constraints dictate that you cannot make that mapping. All right. So once we have applied all of these constraints, and there are more, you need a way to score and rank these sort of candidates. So what we use is something called interspan time distributions. So the idea is that let's say you have a user which is talking to A, and A issues a request to B in order to service it. So we create a distribution that sort of stands for the expected amount of time service waits before it invokes the backend request. And we do this for all the other pairs of endpoints that our application interfaces with. And we use that distribution to basically get probability scores for each of the candidates. All right, so an astute observer might have noticed that this is kind of like a chicken and egg problem because we want time distributions to score and rank our candidates to create span mappings, but we need span mappings to even build the sort of time distributions to begin with. So the way we solve this, and more details are in the paper, is by using an iterative joint optimization process where we start with a best guess seed distribution, which is built out of heuristics. And then we apply all the other things that we know to be correct. We apply the constraints, we rank our candidates, we apply our joint optimization, which is coming up. And then we get one set of mappings from that. And then we use those mappings to build our distributions iteratively. So you can think of it as jointly learning the best kind of mappings that give you the best kind of distributions, which give you the best kind of mappings. All right. Finally, after we get all the sort of valid candidates for each incoming span, we run our joint constraint solver. So what we do here is we solve the mapping problem in a joint manner such that it allows all the incoming spans to get a good mapping simultaneously. Right? So here we're not solving for the dark blue span in a greedy manner. We're solving for all the requests simultaneously so that they can get their mapping at the same time. All right, so in order to do this, what we do is we convert the joint constraint solving task into an instance of a maximum weighted independent set problem. So what's a maximum independent set? It's the largest set of vertices in a graph where no 2 vertices in that set share an edge. So we're trying to find such a set from a graph that we can form. So in this case, 1, 3, and 4, it forms such a set. This is a strongly NP-hard problem, but it's feasible for small graph sizes. All right, so let me give you an illustrative example. So let's say you have a batch of 3 spans, and you have identified the candidate mappings for each one of them. We convert them into vertices of a graph, and we assign scores to these vertices corresponding to the scores we get from the probability distributions. And then we basically add edges to sort of encode our constraints. So for example, here, the orange span cannot be attributed to both the blue and red incoming span. So we add an edge between them so that they're not simultaneously picked, and so on for the yellow span as well. And then we run our solver, which identifies the maximum independent sets from this graph, and we reiterate this process until we get a maximum independent set, which has the highest score, which is where the weighted part comes in. And that implies that we have found the most likely set of mappings for this batch of incoming spans. All right, so once you do this, you can put together TraceWeaver. So this is how it all comes together. So first we collect our raw inputs, which are these test spans, and then we pass it to our sort of call graph inference module, which can basically tell you the call graphs and the sort of constraints associated with these test spans that we collected in our developer environment. So this is like a one-time pre-process phase. Then in the live phase, we basically collect these live spans via eBPF, and then we run a suite of techniques which basically apply the constraints, construct the distributions, do our ranking, and then solve the MIS problem in order to get our fully mapped traces. And this is the reconstruction phase, which is an ongoing phase and runs alongside the application. All right, so now moving on to some evaluation. So our basic evaluation strategy is to sort of check our accuracy across increasing load. So we do that across 3 microservices, where each microservice consists of a set of services. As you can see here, as load increases, all the sort of techniques sort of get lowered accuracy. But TraceWeaver is still able to get a pretty high reconstruction accuracy, which can be pretty useful for a lot of use cases. The baselines, because they do not check for constraints and do not do joint optimization, sort of perform poorly because of high interleaving between spans at high load. We also tested across 15 most popular call graphs in the Alibaba dataset, and we see a similar trend here. Please note that these are traces from the Alibaba cluster, so we cannot actually change the load. So what we do is we post-process the traces to control what load our TraceWeaver instance sees for each of these traces. We also test the trace reconstruction accuracy across a variety of conditions, one of them being the call graph dynamism, where due to caching, you see a different call graph in runtime. So for example, what I mean by that is during analysis, we saw a normal call graph which looked like this, and then during runtime, we saw a completely different call graph because of caching. So that service there did not make that backend call, due to which that span was not seen, right? So we also test TraceWeaver's accuracy on such conditions. And how we handle that is by adding some fuzziness to our algorithm, which basically tries to say that the call graph must be respected as much as possible, but even a subset of the call graph, if it can be adhered to, is OK. And we can see that TraceWeaver still gets pretty high accuracy in these cases. Now, to show what these sort of approximate traces can be useful for, we showcase two cases. The first is this. First is on debugging performance outliers. So for answering questions like which service contributes most delay to the slowest 2% of the requests. So if the developer did not have tracing or even had approximate tracing, all they can do is they can go to each individual service and say, what are the requests in your top 2% bracket, and what are their delays? So what we're plotting on the y-axis is basically the delay distribution of all such requests, which are the top 2% for each individual service. And then with TraceWeaver, what you can do is you can basically plot the delay distributions for all the requests that are in the end-to-end top 2%, right? Now let's see how the ground truth looks like. So as you can see, the ground truth is pretty close to what TraceWeaver gets, which basically means that now if you want to sort of debug tail latency for your end-to-end request, you can basically go to TraceWeaver and ask it which services are basically problematic. So in this case, on the left, if you were trying to debug, you don't know whether to look at search or geo or server profile. You don't know which service to look at to actually go and debug. Whereas on the right side, it's very clear that Rizzo and profile are the culprits. So you can go and fix them in order to sort of reduce your tail latency. The second use case we talk about is A/B testing, where the idea is to ask, does version B improve or regress performance? So usually the way A/B testing is done is that, let's say in this case, you have version B of a service, and you send a small fraction of traffic to that version. The problem is without tracing, and let's say you have two requests, the problem is without tracing, you don't know if request 1 ended up at version A or version B, right? So all you can do without tracing is compare metrics in a world where requests were only being sent to version A with a version where requests were being sent to both version A and B. With TraceWeaver, albeit it's the accuracy might only be 90%, what you can do is you can compare metrics of requests that went to A and B directly, right? Also, the way A/B test is usually done is you run a t-test and you get a p-value. The lower the p-value, the more confidence you have in that test. So for example, you have more confidence in the assertion that version B is bad, right? So as you can see on the plot on the right, the blue curve, which is without tracing, you have to send almost 20% of requests to version B before you can come to the same sort of statistical significance. Whereas with TraceWeaver, which is agreeably sort of imperfect, you can send 2% of requests to version B and get away with the same amount of sort of significance. So the idea is, yeah, even with 90% accuracy, much less traffic can be sent to version B, which is great because now you don't have to expose many of your clients to a buggy version of a service. All right, so I will summarize. So we have presented TraceWeaver, which is about distributed request tracing for microservices without application modification, where we use information which is available for free to reconstruct traces with pretty high accuracy and use these traces to answer powerful queries for performance diagnosis, A/B testing, and so on. So if you have any other tracing use cases, please come talk to us, or you can email me at that email ID. Thank you.
Great talk, Jinrong from Duke. So I just have one question. I don't see why header propagation requires substantial modification to applications, because to me, you just modify the RPC library, because most companies have their own RPC libraries. You just modify the RPC library and insert the headers you need to the HTTP headers, and that's all. So why?
Got it. Yeah. So there are many solutions where either the RPC library is very tightly coupled with the application, or you have library support or language support in order to do tracing. But all of this is like limited support, and also it needs to be super tightly coupled with the application. So think about it in the case where the RPC library is just giving you the request, and then the application is the one that decides where to send this request. So the application still needs to be in the loop in order to do the header propagation. So while the RPC library can still add the headers, tack it on, and so on, the application still needs to sort of propagate it to the backend request. Unless you build sort of applications which are like super tightly coupled with a particular type of technology, in which case the RPC library is in the loop when you do that, but that hasn't got a lot of adoption yet. Yeah.
Okay, I see. Thank you.
So these microservice components of a service are often state dependent. And even if it is a serverless, stateless environment, there's some backend state that influences how you forward to the downstream.
Right.
How much will that impact your accuracy? Because I looked at your cache impact. That has some already fairly significant impact.
Right.
How can you factor that in?
Right, that's a very interesting question. So I think a couple of like future work is on using more state and even like request header parameters to figure out what the ensuing call graph could look like. Yeah, sorry, go ahead.
It's not so much request parameter dependent.
Right.
It could be dependent on the current state of the system.
Right.
How much money is left in your bank account? And that is something that you go dip into a database to find out.
Right. So the idea is that if you have like state-dependent call graphs, that will be reflected in the sort of external information that you can see. So for example, if you're not making certain calls, if you're making calls to like different services, the outgoing spans that you can observe will be like a different count. Like, so it will not be the count that you normally expect in your call graph. So for example, you might expect to see a call to service B, but you will not see it if you have like state-dependent things happening which deviate from the call graph. So these still have like some impact on the externally observable information that we can gather.
So you'd have to do some learning for it.
Correct, exactly. Yeah.
Let's take a last
Sure, yeah, go ahead.
Thank you for your talk, Chang Liu from Tsinghua University. My question is, can your tracing system handle the case where the input of a specific microservice will generate more than one request to different new microservices? If you can handle this case, how can you correlate these requests?
So are you talking about, sorry, it's gone away.
Like one to more?
Yes, so one to more is definitely handled. It's just that for the purpose of illustration, I just showed one backend span, but it could be like n different backend spans that a particular request causes. Yeah.
Okay, thank you.
All right.
Thank you.
All right, thanks.